All right, thanks, Beth. My first time at JCATI here. I guess it's the first time in person, as you said, for a few years, but my first time here. So thank you for inviting me. I know it's pretty varied, and certainly going around the posters, I see such a wide range of topics. And by the way, congratulations to all the students, all excellent posters, I have to say. And so I had initially prepared a presentation that was a little higher level, but when I met with Beth and Meran last night, they assured me that there were lots of people here who would fully understand material science, engineering, composite materials. So yesterday evening I threw in a few extra slides. So for those of you who are not materials gurus, sorry about that, but hopefully for those of you who are, this will be pretty interesting. This is just the overview. I just want to talk a little bit about kind of why we're interested in thermoplastic composites, talk about the materials and the current state of the technology, and then kind of where we're looking to head in the future. Because I think as we've seen from some of the talk, or the one talk today already, a pretty exciting time in terms of a lot of developments going on in aerospace, and some of that is very much related to what we can do with some of the new materials as well. Just wanted to mention the organization I'm with, ATC Manufacturing, because it's not one of the big names compared to the other speakers, who I'm sure you'll recognize all their companies very well. We were founded by a Boeing engineer, so we've always had a very strong heredity into aerospace, and particularly commercial aircraft side of things. He had been involved in some of the early work going on at Boeing in thermoplastic composites, felt it was a very exciting technology area, so he decided to go off and set up his own company. So we have always been focused purely on thermoplastic composites. We don't do any work on thermosets or metals, but all with very high performance thermoplastics. So long continuous fiber materials, not injection molding materials, but real truly structural materials. We're actually located, our facility is located in Post Falls, Idaho, which is just over the state line from Washington into Idaho. However, we have a bit of a foot in both camps because our parent company is based in Washington, and they recently acquired the former Triumph Composites facility, which is by Spokane Airport. So we do have feet in Washington State as well. As I mentioned, we've always been focused on aerospace, so we have all the normal aerospace standards, and have typically worked pretty closely with Boeing over the years, with some of our awards, as you see there as well. We are a member of the NASA High-Rate Composites Manufacturing Program. We were brought into that specifically because of our expertise and the interest in thermoplastic composites there. And as well as doing development work, which I'll be talking about some of that today, we are also a high volume manufacturer. As I say there, we've supplied over 1 million parts per year into aerospace applications. So let's talk about kind of why we want to get into thermoplastic composites. So the chart at the top here is from Rick Young, who is the program manager for the NASA High-Rate Composites Manufacturing Program. So this is his interpretation, or NASA's interpretation. And I should say, when he's referring to composites here, he's really talking about the current incumbent materials, which is pretty much toughened epoxy, carbon fiber, prepreg type materials. So he's highlighted some of the trade-offs between the metals and composites. And obviously composites offer many advantages, weight obviously being one of the primary ones, one of the reasons for that. Also the fact that we can make use of the anisotropic properties in terms of design, particularly things like the thin wing that he highlighted here. Maintenance costs, which is actually, I think, a bit of one of the unsung benefits of use of composites, that really airlines who have been operating aircraft with high degrees of composites find that there's much less maintenance, corrosion, related things using composite structures. But as he identified, composites, at least the current incumbent epoxy or thermoset-based composites, don't really meet very good in terms of production rate or the acquisition costs. So that's one of the areas, or a couple of the areas that we really want to attack as we're going forward in the future. And so some of the attributes of thermoplastics, obviously being composite materials, we're looking at light weighting. They certainly offer some benefits in terms of specific performance areas, especially toughness, flammability as well. The polymers we're working with are very low flammability. Cost effectiveness in terms of very fast cycle times and therefore lower overall fabrication costs, and of course can meet high rates. In addition, I was talking to some of the poster sessions involved with recycling there. Very interesting that with thermoplastics you can recycle them. I should perhaps more accurately say downcycle, because you can take the thermoplastic composite and often chop it, shred it, combine it with other polymer, and then compression mold or injection mold it. And indeed, another side of that is some of the materials we're working with, not so much in structural applications, but more on the interior side, actually use recycled carbon fiber as their input material going into that. So thermoplastics can certainly kind of bridge some of those attributes of both the metallic structures and composite and current thermoset composites. Just another chart kind of related to this. The chart on the right here is from Randy Wilkerson, who's a Boeing Technical Fellow based in St. Louis. This was presented at the American Composite Manufacturers Association conference in 2020. It's part of a program that Boeing did under DARPA funding called RAPM, Rapid High Performance Molding, in which they looked at a number of different technologies around thermoset prepregs, infusion, and thermoplastics. And from that, looked at the recurring part cost of using different materials and technologies. And so certainly for small and medium-sized parts, their conclusion was thermoplastics really offer a pretty compelling advantage, in many cases even over metallic parts as well. Of course, some of that comes from the handling of the materials. Thermosets require frozen storage, out time issues with thermosets. You lay them up ply by ply, whereas with thermoplastics you can do much more automated processes. Other aspects that I mentioned, performance, and we'll also come on to assembly and recyclability as well. So certainly thermoplastics can offer a really compelling advantage over some of the current materials. Of course, the obvious question is, so why aren't we all building planes out of thermoplastics now? Well, some of the materials have not been very readily available. We're talking about very high temperature processing often with these polymers. And the process technology to both impregnate the fibers with these very viscous polymers and then to turn them into a finished part is one of the areas that's really been developing over the last kind of couple of decades. So let's talk about some of those polymers. This is a pyramid of polymer performance that you'll often see quoted around. So we have more the commodity polymers at the bottom end that are used in very high volumes. All around us, some of the very, very common and low-cost polymers, polyethylene, polypropylene, and so on. Then more into some of the engineering polymers, things like polyamides, nylons, that is, or PET materials, up into polyphenylene sulfides. And then up to the very top area of the peak of the pyramid there, which is also a peak polymer, often polyaryl ether ketones, so peaks, PECs, low melt PAEKs. And a big part of the performance driver for these is the combination of service temperature and mechanical performance. So a lot of the polymers that we're looking at in these applications are at the very top end here, the high end of the engineering polymers, and really into what we'd consider the higher performance polymers, with both high service temperatures, but along with that, high processing temperatures. And you'll notice these polymers are on this sort of right-hand side of the pyramid here, because typically we want to work with semi-crystalline materials. because they have much better environmental resistance. And so these polymers that I'll be talking about in some of the talk today all have very good resistance to all the environments you'd come into contact with in aerospace, things like jet fuels, de-icing fluids, hot hydraulic fluids, and even in the space area, things like liquid oxygen. These materials are very, very resistive to that and very tough as well. When I talk about the range of product forms, then, so we're then taking that polymer, combining it with a fiber into a composite material. Of course, there's quite a wide range of composites you can make, everything from the very short fiber materials, which can readily be extruded, injection molded, compression molded, through to the very highly reinforced materials that are equivalent in terms of fiber content, fiber orientation, to the state-of-the-art thermoset prepregs. So things that are up in the region of kind of 60% fiber volume, unidirectional tapes. So when we're looking at this context with aerospace composites for structural applications, I'm really talking about the things at this very left-hand end here that are really pushing the performance. Although, of course, with that, there's limitations in the manufacturing flexibility with continuous fibers and again, very viscous polymers. Now, there are quite a range of materials available now. If you went back maybe 10, 15 years ago, the amount of materials that was available, or the range of materials, was extremely limited. There's maybe a choice of like one unidirectional tape and a couple of fabric materials, and that was about it. Now there's quite a wide range of different composites available, starting with kind of fully impregnated unidirectional tapes available from quite a wide range of suppliers and with many different polymers. There's a illustration down here from the Thermoplastic Composites Research Center people that I realize might be a little hard to see, but this is photomicrographs across 3 different prepregs from 3 different suppliers. And nominally, these are the same polymer, the same type of fiber, the same fiber aero weight, the same resin content. And yet, the fiber resin distribution can be very different in them depending on the prepreg technologies that are used. And this is one of the things that I'll be talking about, the interaction of the material or the product form of the material, and the processing is often very key with thermoplastic materials. And just to show that, you'll see there's quite differences in terms of the uniformity of the thickness, the fiber resin distribution, the degree of impregnation. So those are fully impregnated materials. Again, maximum performance. But not always the easiest materials to work with in that they're not drapable, they're very dry, body materials. The next one is partially impregnated or semi-preg materials that typically have something like a powder or a commingled fiber of the polymer with the reinforcing fiber. So these can have an advantage that they are drapable at room temperature. But of course, then you have to impregnate that polymer into the fiber during the process cycle. So you gain the advantage of much easier handling in terms of laying up a part or draping it over a complex tool. But typically longer cycles, again, because of the viscosity of the polymers and actually wetting out the fibers. And then the final form that has often been used is laminates, or what are often referred to as organosheet. So these are fully consolidated laminates that are available in set layups with the fabric reinforcement. So again, the advantage is they're fully impregnated, the layup's already defined, you just have to cut a blank out of it and form it into a finished part. But of course, there are limitations in terms of the size that you can get, and also you have to specify the layups, for instance. So basically quite a wide range of material forms now available in terms of the polymers, the reinforcements, and the overall product forms. So as I mentioned, you've sort of got this trade-off of the fully impregnated forms that can be processed very quickly because the impregnation has already been done, the fibers are already fully wetted out. versus the partially impregnated forms, which have the advantage of handling and drapability at times. But again, you have to impregnate them during processing, which means it's a longer time. The materials are maturing. Again, things like the consistency of the prepregs, degrees of impregnation have definitely been improving. And another point is around databases. Of course, when we're talking about aerospace, we typically need certified databases, design allowables. We'll need material specs, process specs. And until recently, that's sort of been the domain of a lot of the OEMs who have the horsepower to be able to generate that information. But now we're seeing more and more materials are being in the MCAMP databases. If you know those out of the NIAR, the National Institute of Aviation Research at Wichita State, which has standard specifications and databases. So I think there's now three thermoplastic materials that have full NCAMP quals, and quite a number more that are in process. So that means that the information on, again, kind of properties, design, process specs, are more coming into the general domain and can be used by anyone. This is publicly available databases. So if we talk about some of the initial applications for thermoplastics, again, this is going back a while, kind of 20 plus years or so, when some of these materials were first coming out. Some of the emphasis initially was much more driven by performance, particularly toughness and temperature. And so as an example, on the far left there, the F-22, the weapons bay doors were made out of thermoplastic, actually a peak IM7 material. Also over in Europe, the Dassault Rafale, the internal center fuselage section was done in thermoplastic, again, a peak material. Some of the reasons on the Dassault was because it's around the area of the engine. They were looking for both high temperature performance and flammability resistance as well in case there was an overtemp condition. Also over in Europe, with some of the fabric materials, they were adopted by Airbus and GKN for the leading edges, the inboard for the U340 and the outboard for the U380. Again, that's been kind of pretty well publicized, a lot of information on that. But I'd characterize some of these initial applications as more sort of the point applications, where people were really learning how to process the materials, especially at that stage, often using techniques that were borrowed from thermosets in order to form the finished parts, which was really not the optimum in terms of either cost or rate. But it was important in demonstrating some of the early applications of thermoplastics and the benefits of them. So if we then come on to kind of where how we're making parts today, which has progressed since that time, we're typically starting with the material preparation. Again, these are dry body materials if we're starting with the prepregs. So we have to have ways to take those prepregs, assemble them, often with highly automated processes into the layups that we need. To get the plies assembled, because you have to tack those plies together. The materials don't have any inherent tack, so you're often using either thermal or ultrasonic tacking to prepare that. And then very automated processes to make a laminate or a blank, which is then thermoformed or stamp formed, usually rapidly formed into the finished part, or alternatively going through a kind of one-step process directly from the ply layup into the finished part. So these elements are sort of the things that are specific to thermoplastics. I've left the back end on this as well because, of course, you still have to go through all these processes. There are some differences in how you do those with thermoplastic composites compared to thermosets, but you still have to go through those. So the real sort of benefit, particularly in terms of costs and rate, are in this part of the process of really getting your material prepared and then turning it into the finished part. Some of the challenges with thermoplastics at times can be that there's actually a lot of different ways of forming them into a finished part. So it's like, if you come along, like what's the right process to use for a particular part and application? So that I think is confusing at times, and one of the reasons why thermoplastics have had somewhat slower adoption as well. If we then come on and talk about where we are in terms of current applications. So in parallel, I would say, with some of those initial point applications, there were folks, particularly in some of the higher volume uses, like commercial aircraft, who identified that there was very good opportunities in quite simple parts that get used in high volumes. And especially as both 787 and A350 came along, there was strong desire to use all composite structure to avoid issues of, as an example, aluminum next to carbon fiber composite and galvanic corrosion issues. So a lot of these kind of smaller detailed parts that historically would have just been out of aluminum, there was a big driver to convert those over to composite. And thermoplastics was kind of the ideal material there for these high volume, smaller, more detailed sort of parts. So typically kind of clips and brackets down at the bottom here. This is one of the A350 frame clips. That was one of the big applications on A350 with many thousands of those on one aircraft. And then also into some more complex parts, a kind of deeper drawn continuous fiber part here, which is a stiffener, channels, and then into full structural components. Indeed, there are primary structural components flying around now out of thermoplastic composite unidirectional tape materials, and indeed full assemblies. GKN Fokker, the GKN name will come up a lot in the Netherlands. This is the Gulfstream G650 rudder, and they have done a lot of work developing that with PPS fabric materials and using welded assembly for that as well. So again, these are flying around, many millions of parts actually in service now, although they're in the areas that you wouldn't necessarily see. They're the bits that hold other structure together or hold hydraulic lines or electrical lines throughout aircraft. So in terms of the current status, thermoplastic composites are now pretty well established in a lot of these kind of small to medium-sized parts, generally the higher volume applications. But I'd also say they often have been limited at this point to constant thickness parts. And that's the practicality. We're often preparing a laminate or a layup that is then going to go into a forming process, so they tend to be constant thickness. And somewhat simple geometries. Again, things like the illustrations here, the L's, the open sections here. This is a deeper draw part, which is a little more complex, although it's not as structural. So they have a certain niche that's already quite well established. But really the question is kind of where do we go to in terms of the next step? And that's where I think is kind of pretty interesting, where I want to concentrate the rest of this discussion. So in terms of the future, we're really interested with those benefits, particularly of cost and rate, of now starting to look at much larger structures. So skins. This is a demonstrator from Europe, from the Clean Sky program, and I'll actually come back to this, of quite large area skins with the fuselage and fully integrated structure. Along with that, things like window frames, ribs, fuse frames, floor beams, spars. So a lot of interest in these sort of parts. They're still relatively high volume. Obviously, the design often gets tailored throughout the aircraft. So it's not like there's necessarily just one floor beam all down the length of the aircraft. But even so, there's a limited range of different designs. So it really lends themselves to high volumes. Similarly with things like fuselage frames as well. Again, a lot of there can be different designs along the aircraft, but really high volume that can be adapted very easily for thermoplastics. And also going for a much more integrated structure. As I mentioned, a lot of the parts so far are constant thickness. So of course, as we move into more structural applications, we really want to optimize the design and the weight. And so you want variable thickness parts. You want to be able to accommodate very complex geometries where you may be putting joggles, other features, compound curvatures in, which again are hard to form in a continuous material that you're rapidly shaping into the finished part. Assembly, obviously welding is a big opportunity with thermoplastics because they can be melted and welded, and already examples flying around of that, but really taking that to the next level. A lot of what's been done in welding so far has been basically kind of flat structure, and often with fabric materials as well, which lend themselves more readily to some of the welding technologies. And then we're also talking about high volumes and tied with that high rates. And if we look at some of the applications, you know, we're looking at kind of next generation commercial aircraft, as we've heard, advanced air mobility, things like the delivery drones of all sorts of sizes, from the smaller like Amazon delivery drones up to things that are to deliver much more, like the Bell program here, which can deliver up to an 80-pound payload. And of course, the unmanned drones, which we also already heard about as well. So all of these, we're looking at relatively high volumes compared to a lot of aerospace applications. Just to talk about that a little bit, though, we kind of got to put it in context, because there's often a lot of discussion about, you know, aerospace quality at automotive rates. That's often a tagline. But just to kind of put that in context, if we look at current rates, as an example with 787, 160 a year. In fact, on record, the largest number of 787s that were ever delivered in one calendar year was 2019, and that was actually 158 were delivered in 1 year then. So that's kind of a bit of the context of current composite kind of production rates for state of the art. Where we're looking at for the kind of next generation sort of narrow body aircraft and also the advanced air mobility, you're probably looking at about 1,000 vehicles a year. That's the kind of nominal production rate. Obviously, within that, you may have components that are not just one per vehicle, but are used many times. So the actual rate of an individual part could be a lot higher than that. But then if we look at kind of the high performance auto end and take a Corvette as an example, it's at like 25,000. That would be a typical production rate for that. So we're talking about roughly a sort of order of magnitude here as we go from kind of where we are now to where we want to be. But if we're talking about automotive, even high performance automotive, it's yet another order of magnitude. And so we're sort of in this middle ground between what you might consider something that's more a cottage industry at one end compared to something that you can really fully automate at the other. At this sort of range of, you know, about 1,000 parts per year, you've really got to kind of look at what's the cost of getting to full automation, you know, what's the business case related to that. So it's kind of an interesting, I think, industrial engineering challenge as well. So in terms of how we're going to change things, again, a lot of the parts we've been making to date have been kind of small to medium size, a few feet in size. We're talking about getting the much larger parts, larger structures. So how do we do that? Well, first of all, we really have to move to automated processes, and fiber placement is kind of the most obvious one to move to. There's been a lot of development work going on right through the supply chain of people who build AFP equipment to developing materials that are more suited for fiber placement, through to the OEMs doing development work, and indeed the government agencies. NASA's actually done quite a lot of work on thermoplastic AFP. Obviously, one of the advantages is we're essentially kind of unlimited in terms of the size of parts we can make. Obviously, AFP is very well established with thermosets, been used for decades now. So some of the same approaches, of course, can be used, particularly with topology, layout patterns, and so on. The key difference is how do you get the material down and consolidate it? With thermosets, you typically heat them up a little bit, often infrared heating, just to reduce the viscosity, improve the tack as the plies are being laid down so that they'll adhere to one another. With thermoplastics, you're sort of in a different realm of temperature that you've got to get up to 700 Fahrenheit plus, right in that nip region. Just to highlight some of the local folks here, of course, Electro-Impact just up the road in Mukilteo, they have developed laser head. Different heating techniques have been used, although I'd say the sort of consensus right now is really around laser as being the best way to really focus in just on that nip point where the materials are being laid down and to be able to control the temperature very precisely there. Just to mention, Electro-Impact does have quite a sophisticated head that will actually look at the temperature at each individual toe of material being laid down and will adjust the temperature input based on that, and also on the laydown rate. So when you're starting, it'll put less heat in, and then as the head is traversing and speeds up, it'll actually increase the energy input in order to keep the melt temperature consistent. So a lot of sophistication there. But of course, pretty much all the manufacturers of AFP equipment are developing heads. I'd also highlight Coriolis, another one that has been working on this for a long time. This is at the Daher facility in Nantes in France. So they're also working on it. And here, this is again part of one of the European projects. Actually, it's related to the Clean Sky, but it's called STUNNING, which is an acronym I won't go into now, but it is an acronym. And this was done at the NLR facility in the Netherlands. And this is certainly touted as being the largest single composite structure. That's about an 8.2 meter long skin that was laid up as part of the fuselage demonstrator that they were doing in Europe. With again, single piece fiber-placed skin. There's been, for quite a long time, people were really trying to get to complete finished structure through an AFP process. So true in situ consolidation, you get full finished part quality off the tool. The consensus, I would say now, is that can be achieved, but it's just not economical. Even NASA, who have put a lot of effort into this, have really come to the conclusion that you have to slow down the laydown rate so much to be sure of getting full consolidation and also full control of the crystallinity. As I mentioned, a lot of these polymers are semi-crystalline. And so when you're laying the material down and you're going through another thermal cycle, every ply you lay down, ensuring you're getting a uniform crystallinity in the material is a challenge. And so the way the industry's really moved now is to say, we'll target getting a pretty high degree of consolidation, something in excess of 90%, but we're not going to worry about getting perfect consolidation, because if we can get to 90%, then we can really increase the laydown rates to things that become economical and comparable with thermoset laydown rates. And then we'll take it into a final process in order to get the final kind of full consolidation of the part. I will say as well, again, interaction of material to process. You really do need very high quality tapes here, because the laydown process obviously is happening very quickly. There isn't time to really deal with any porosity that's left in the individual toes of material. And so you do need materials that are very well impregnated, very uniform in thickness, very uniform in fiber resin distribution. And so that has been a big driver for some of the materials developments as well, to get much more consistent products that can then go straight into the AFP process. The other thing you can use AFP for, obviously, is to build up different ply thicknesses, but also to steer the plies. So this is actually out of some specific work we were involved in, which was initiated through Spirit. They were the lead for this, but this was specifically looking at fuselage frames for a demonstrator they were building. So this was a partnership with Spirit, Electro-Impact, and ourselves. So if you imagine the blank that you need for a curved fuselage frame, it would be roughly this shape. And if you took a kind of, if you like, simplistic or traditional attitude, you would just lay it up in your usual sort of 0, 90, 45 layup. But of course, that means the fiber orientation is effectively changing constantly around the curvature of the frame. So what electroimpact did was to enable steered plies. Again, something that's been established in thermoset materials for some time, but in the thermoplastics with the very rigid body input material and the very viscous polymers, that's not something that's very straightforward to do. But electroimpact came up with the process to be able to steer, as an example, the 0-degree plies around the radius, and the 90s and the 45s, so they were radial. This also incorporated variable thickness. So this is actually from the model here. So I'm not certain if you can tell, but the inboard side here is actually quite a bit thicker than the outboard area that mates to the fuselage. And the ply drops buildups are all in this web area here. So electroimpact actually made flat blanks, but with the steered plies, which at ATC we then took and stamp formed into the finished part. So this is actually the finished part. This is the model. This is the finished part here. Obviously, the geometric tolerancing on the outside of this has to be very precise as well, because that's mating directly to the fuselage. So your tolerances there are extremely tight. And so that's been part of the challenge of managing a lot of the thermal processes to really get very tight GD and T. Another area that's been advancing. So this is a demonstrator. Again, this was publicized kind of last year at one of the industry conferences. If we're going to take those AFP layups or indeed other ways of consolidating the plies, or preparing the plies, I should say, you then still have to consolidate them or form them into a finished part. And if we're talking about big parts, it's like, okay, how do you actually do that? So several options here that are all being looked at. So there's large-scale stamp forming. Again, big presses are sort of readily available, been used for many, many years, particularly in the metals industry for stamp forming of parts, of course. We can use some of that same technology, but with a lot of provisos. First of all, we're sort of heating a blank that has to be at a very precise temperature, moving it across to the stamping station. You have to use a heated tool. It also has to be at a very precise temperature. And the tools that you're stamping it in also have to be very tight dimensionally controlled. So while you can use some elements of existing technology, there's a lot of other things you've kind of got to look at in terms of how you're going to manage this. But it is an area that's being really looked at very actively. As I mentioned here, Airbus has actually announced that they're putting in a 5-meter, 3,000-ton press at the Bremen facility in Germany, specifically to stamp form thermoplastic composite structural parts. The sort of other extreme in terms of pressures, if you like, is just to go to vacuum consolidation. Again, if you get a highly sort of compacted blank, typically with an AFP process, then you can probably get that to full consolidation. And there's been a number of kind of demonstrations of that, either purely in an oven, again, with a kind of reusable bag, or as an example, you can actually use autoclaves, but rather than using the normal heating of the autoclave, you'd actually put in heat a bank, which will just heat the local area in order to get the material melted and again flow. This again depends on having a pretty high quality blank to start with though, because by definition, if you're only doing it under vacuum pressure, you don't have a big driving force to move that viscous polymer. So you need to have, again, a pretty low porosity blank, a pretty well consolidated blank to start with. But again, that can be a very economical process. Another thing I'd mention is the idea of using integrally heated tooling, typically with pixelated tools. Now, traditionally, if you take a big solid tool, it's going to be extremely slow to heat up and cool down. I mean, that's one of the things we see, of course, in thermoset processing in the autoclave. But with the idea of this sort of pixelated tooling, example here from Surface Gen out of the UK, where you break the backup down into certain elements, maybe about 3 or 4 inches, and then you can heat each of those or control the temperature of those individually, either with a gas or a fluid that is actually ducted directly to that little pixel. You can both heat up and cool down quickly, and you can also control the temperature very locally and very accurately. So as an example, if there's a thicker part of structure, you would want to put more heat into that area. This, as I said, this is out of Surface Gen. Certainly Boeing Research and Technology in St. Louis has one of their units. And also locally here, JCATI has been developing some similar technology as well. So again, a lot of methods available, a lot of development work going on right now to really prove those out as to which is the right one for which types of parts, whether they may be, say, skins or much thicker parts. Welded assembly, there's various techniques already available for welding that have been proven, certainly on the smaller scale, even at production levels, with resistive welding, induction welding. A lot of the induction has been done with fabrics because you typically don't want to use a susceptor in there, which puts a defect into the weld zone. And in terms of inducing the current and therefore the resistive heating in the weld, fabrics, of course, lend themselves much more because you get the induction loop created. Unidirectional materials is more of a challenge, and there's quite a lot of R&D work going on right now to really be able to characterize that and focus the heat into just that area of the weld. And then another approach, of course, is co-consolidation. Again, GKN has kind of championed this, of making multiple small parts and then co-consolidating them all together in a structure. This was some of the work they did for a demonstrator wing rib, made up of quite a range of different elements, particularly using simple shapes, often flat, straight shapes, which don't need their own forming, but joining these often with kind of short fiber reinforced parts, but then getting a full integral structure by going through the whole co-consolidation process. And I just mentioned briefly process modeling. We've kind of touched on process conditions a little bit. And how we control that, because of course we're starting off at quite a high temperature, in excess of 700 Fahrenheit. Cooling down, the polymers become more and more viscous. You hit a crystallization point, which is solidification, stress-free temperature. You also see quite a large volume change, of course, at that point as the material crystallizes. And then a couple of regions of temperature performance as well as you cool down through the TG. So modeling that and particularly relating that to the fabrication process is really important. And then the ply orientations, as we've seen in the illustration here on the right. So developing modeling software tools that are really specific to thermoplastic composite forming, which really draws a bit on isotropic materials like metal forming that's been done historically, combining that with some of the composite forming approaches. So finally, kind of conclusion then, thermoplastics can certainly offer advantages in terms of the cost and rate. The kind of small to medium-sized parts are really well established. Quite a wide range of fabrication technologies. We're certainly seeing a lot of maturing of the process science. And the kind of MRL levels for large structures are really starting to develop pretty well. And the need to match the product form and quality to the fabrication method and design for manufacturing approaches, particularly tailored to rapid forming of thermoplastics. And if just a couple of examples here, of some of the large-scale development programs going on. I mentioned this Clean Sky program, the Multifunctional Fuselage Demonstrator, MFFD, that there's been quite a lot of publicity coming out in the last few months. This is actually the full-scale demonstrator using that 8-meter-long skin with all the integral structures here, the floor beams and all the other frames, stringers and so on within it. The NASA HICAM program, which is only about 18 months into a 7-year program, so that's actually going to be demonstrated in a fuselage section and wing section as well. And just mention one last thing, if you are interested in thermoplastics, I think we've already have mentioned the SAMPI conference is actually right here in the conference center in downtown Seattle next week. In addition to some thermoplastic sessions, the JAMS, the FAA JAMS sessions will be on there, and there'll also be papers from the NASA HiCam program. And then about a month out in May, Composites World is having a virtual tech day specifically on thermoplastics for large structures as well. So a couple of things coming up there. So thank you.